So let's see, where'd we leave off yesterday?
I think 7.15
Okay.
at the beginning.
I seem to remember doing at least one out of that. Maybe not. Let's try that.
I don't know.
Oh, yeah, I remember looking at this, but I don't think we did anything. Did you try their experiment? What kind of calculator do you have?
84.
Okay, that's pretty easy to switch back and forth between degrees and radians. You know how to do it?
Yeah.
Okay. So do you know how to manually convert? What's pi over 4 equal to?
Like angle-wise?
Yeah, well, that's in radians. When you see a pi, it's generally in radians. What degree is that?
45.
Yeah, there's something that's really worth knowing if you don't know it. Let me just go through it real quick. Makes it really easy to switch between radians and degrees. Pi over 2 equals 90. Pi over 3 equals 60. Pi over 4 equals 45. These are all degrees. And pi over 6 equals 30. You see the magic? Those two numbers multiply to 180. Those two multiply to 180. Those two multiply to 180. Those two multiply to 180. So as long as you just have a pi in your numerator, it's a terrifically easy conversion. What if I said 2 pi over 3? If pi over 3 is 60, what's 2 pi over 3 got to be equal
to? 120.
How about 3 pi over 4?
I can't think. 135.
Right, 3 times 45, right. So if I said 7 pi over 6, in other words, these are the kind of problems that give students fits. But if you do it this way, it's pretty easy. In other words, as long as you remember those right there, then you can do any of the complicated ones that they ask by just multiplying that by 2 or that by 3 or that by 7. Now, there's a more official way of converting, and that's by using the conversion factor, pi over 180 or 180 over pi, depending on which way you're going. But if you're going from radians to degrees, I defy anybody to come up with a simpler method than the one I just explained. Don't have to use that conversion method, nothing. You just have to know that the denominator multiplies to that to be 180. So you really only have to memorize that single fact. In other words, that single fact lets you know this one, and that one. All right, let's go on. Part B. This has to basically do with the unit circle. You know what? Do you know the answer to part B?
45 degrees.
Well, yes, but there's also an angle in the second quadrant. We did the unit circle, right?
Yeah.
The other day. Remember the unit circle. 45 degrees, the sine of 45 degrees is square root of 2 over 2, but the sine of 135 degrees is also that. Notice that the 135 degree makes that reference angle 45 degrees. And also, in the second quadrant, we do 180 minus theta to figure out what the equivalent angle is. So, and then we know all students take calculus, so sine is positive in the second quadrant. Therefore, the sine of 135 degrees equals the sine of 45 degrees. And to put it into radians, it would be the sine of 3 pi over 4 is the same as the sine of pi over 4. Now, when you get into radians, I can convert that to radians. That's pi minus theta. This is theta minus pi, and this one is 2 pi minus theta. So there's no trouble with radians in terms of figuring out the equivalent first quadrant angle. Just use this. In other words, for pi over 4, I would substitute it into there, and I would get 3 pi over 4 as my equivalent angle. All right. That was 77-77. Yesterday it let me do that. Today it's not letting me do that. Huh?
It was 0.5.
Oh, that's probably why. Yeah, I guess. I'm not sure. Okay, calculate each of the following values. Express your answers both exactly and as decimal. So what is the sine, the exact value of this?
45 degrees.
Well, it's the same as the sine of 45 degrees, but remember, when we take the trig function of an angle, we get a ratio. What's my ratio?
0.01.
Hold on. We need the 45-45 triangle, right?
Oh.
Since we're talking about a 45 degree angle. Got
yeah, so it's
right triangle. You got to memorize these dimensions. Just no two ways about it. So that's 1 over square root of 2, which is the same as square root of 2 over 2. Okay?
Okay.
So that's the exact answer. Now they also want the decimal approximation. What's square root of 2 divided by 2 on your calculator?
0.71.
707, actually. I guess she had to round off to the nearest hundredths always.
I just usually do, so.
All right. Next one. Sine of 2 pi over 3. What quadrant is that in?
The second.
Right. In other words, remember that's pi over 2. That's the same as 90. That's pi, same as 180. And that's 3 pi over 2, same as 270. So when I'm trying to figure out what quadrant, I have to figure out what is this number between pi over 2 and pi, and the answer is yes, it is. So there's my angle. That's 2 pi over 3. What's its equivalent first quadrant angle? In other words, what is alpha? Remember, it's pi minus theta. What's pi minus 2 pi over 3?
Uh,
Pi minus 2 pi over 3. Find a common denominator. What's the common denominator?
3 or 1.
Okay, so express that with a denominator of 3.
Negative pi over 3.
No, not negative. 3 pi over 3. Isn't 3 pi over 3 the same as pi?
Yeah.
Okay, now what's 3 pi over 3 minus 2 pi over 3?
1 pi over 3.
So that's what that angle is, and that's what we're really looking to take the sine of, is sine, the equivalent first quadrant angle is pi over 3, which is 60 degrees. What's the sine of 60 degrees?
0.5, or
Right.
the square root 3 divided by 2.
And what is the plus or minus sign in the second quadrant?
It's plus.
Okay. And what is the decimal answer for that?
0.866.
Okay. Now, I write this in a rather peculiar way. I don't want to say that the sine of 2 pi over 3 is the same as the pi over 3. In other words, I don't write it like this, because sometimes it isn't the same. What my intention here is to tell you what the equivalent first quadrant angle is. And so I put it in parentheses. And then the way we come up with that part of the number is by doing the first quadrant angle. But the plus or minus sign comes from knowing the quadrant you're in. So it can frequently be a minus. So the sine of this doesn't necessarily have to be the same as the sine of pi over 3. And that's why I put it in parentheses. Always. Alright, so if I want to go backwards, I just go to... Well, now yesterday I was doing that and it worked just fine. I only had to do one mouse click to get to the next problem. And now I'm back to having to do 4 mouse clicks. What gives? I wonder. Well, now let me see if I can go back to that. No, they don't let you go back to it. You got to remember which one you did. Guess we did 778. Okay. Show how the zero product property can be used to solve each of the following. Well, that's not even trig, that's algebra.
Yeah, it kind of goes back and forth.
Yeah, that's fine. I like that. How do I solve this?
Just, well, x equals 3, 0, and 1/2.
Alright. And you got that by applying the zero property product. The zero property product says that if you're multiplying any number of things together and the product is 0, then each of those things could be 0. At least one of them has to be 0. Okay? How about this one? And remember what they want us to do. They want us to use the zero property rule. So what does that tell me I got to do? Right now,
factoring.
yeah, right now I don't have very many products going on. I got this being added to this and this being subtracted from that. So for me to use the zero property rule, I got to get some stuff being multiplied together. That involves factoring. So what's the first step to factor this?
To take out an x.
Greatest common factor. What's left?
2x squared plus x minus 3.
Now let's see if we can factor that. Well, it's clearly 2x and x. What are the signs?
Plus 3, or 2x plus 3 and x minus 1.
Yeah, well, yeah, when I said what are the signs, they're opposite. That's what they are. Now, in this case, I don't necessarily know it's plus minus is not the same as minus plus. And you have to be aware of that when you're factoring. Plus minus is only the same as minus plus if the coefficient on the x terms are the same. In this case, they're not. And so every time I factor one of these more difficult quadratics, I always check by multiplying the inside together and the outside together and making sure I produce the middle term. That's the term that everybody gets wrong, is that middle term. So always check that middle term, add them together, you get plus x, that is our middle term, we did it right. Now what's the answer?
X equals 0, negative 3 halves and 1.
Good. Now, oh, I know what I did. I got to click there. I was going backwards. That wasn't the way to do it. I wanted to click there. Now I get presented with 780 immediately. Yeah, okay. I just had to remember how to do it. All right, solve each of the following. How do you normally solve exponential equations?
Log usually.
Correct. So how do I solve this? This is an exponential equation because the variable's in the exponent. That's all it takes to be an exponential equation. If the variable is on the algebra line, then it's an algebraic equation. And you cannot solve an exponential equation using algebra. There is no algebra that will let me solve this. But there are logarithms. So what's the next step?
You take the log of both sides.
Okay, and you can take any log you want. I like natural log. And it doesn't matter. You could take common log. You could take log base 5. May seem like it's more efficient, but it actually isn't. What's the next step?
You put the x in front of the ln.
Now I got x natural log of 5 equals natural log of 72. What's x equal? Exact answer? Not a decimal approximation?
2 point.
Exact answer?
Well,
Natural log of 72 divided by natural log of 5. That's an exact answer. In the same way that square root of 2 is an exact answer, 1.41 is an approximation. Now give me the decimal approximation of that.
2.657.
All right. Now, you say, well, wouldn't it have been better to take log base 5 of each side? Well, let's have a look at that. If I did log base 5 of the left side, I immediately get x. But now I got to do log base 5 of 72. So the left side immediately becomes x. But now I've got this thing that I can't even get that number out of the calculator without using change of base. So I got to use change of base formula, which gives me log of 72 divided by log of 5. So it's really no more efficient. You still get the same answer. Incidentally, this ratio is the same as what I got, natural log of 72 divided by natural log of 5. Those log ratios are always the same no matter what the base is. In other words, this is also equal to the log base 17 of 72 divided by the log base 17 of 5. So that's why it doesn't matter when you say take the log of both sides, which log you use, and why I always use natural log. All my answers are going to end up natural log ratios. All your answers would probably end up log base 10 ratios, which is just as good. No difference. But if you do it what looks like the easiest way, then you have to know the change of base formula. Not everybody remembers the change of base formula. So it's actually better to do it the way I did it in the first place. All right, next one is 2 to the 3x equals 7. Solve that.
Log of both sides.
Now what?
Put the 3x. I thought it was 2x. Was it 3?
Yes.
No, it's 3. Okay.
Okay. What's x equal?
Do you want like the actual or the decimal?
Actual. Exact. I always want exact. I never want the decimal.
Okay, then natural log of 2 or natural log of 7 divided by natural log of 2, all divided by 3.
Well, and that means that.
Alright.
Okay? In other words, I'm really in one step dividing both sides by that. Those are two different numbers. That's all they are. Okay? So I can do it like this. And now, that's kind of interesting because now I can take the 3 and make it an exponent. And what it really is the natural log of 7 divided by the natural log of 8. See how you can do that? If you end up with a number there and as all you have is a number there, then you can simplify that by moving that coefficient back to the exponent. Now, I don't know that you need that answer. I bet you'd get full credit even if you gave this first answer where 3 was in front like that. I don't think you'd lose points for that.
Probably not.
This is a prettier answer, you got to admit. Okay. And the last one is 3 to the 2x plus 4 equals 17. Notice, whenever I'm writing an exponential equation, I leave room. I don't put that 17 right next to the equal sign because I know I'm going to have to take the logs of both sides. So this time I'll take the common log of both sides. Now what's the next line?
2x plus 4 log 3 equals the log of 17.
And the next line?
X equals.
Now let's do it one step.
X plus 4.
What's 2x
Log
plus 4?
17 divided by log 3.
Okay. Now we're going to subtract 4 from both sides. Now we're going to divide everything by 2. Well, dividing everything by 2, I'm going to put a 2 there and a 2 there. Now I can actually simplify that, and probably should. You might lose points here with this answer because 4 over 2 should never be given that way. So if I were to simplify the entire thing, becomes log of 3 squared, which is log of 9. You see where I get that?
Yeah.
That's the best answer right there. All right. I think 780 was the last one of that, wasn't it? Nope. 781. All right, so where did he make his mistake? Let's go through each step. Y equals 2x squared minus 6x plus 2. And he put parentheses around that. And then he factored out a 2 so that the coefficient of the x squared term would be 1. That looks pretty good. Now I'm leaving space to complete the square. So far I haven't changed anything. That's the key. Now he takes half of this term, which is 3 halves, squares it, and puts 9/4 in that spot right there. But then he balances it out by subtracting 9/4. What should he subtract? How much did I add to the right side of the equation when I wrote 9/4 in there?
2.
2 times 9/4. Everything in this is being multiplied by 2. So if I write a number in there, I got to multiply it by 2. That's what I really added on the right side of the equation was 18/4. So I got to subtract 18/4, not 9/4. That's the mistake he made. He only subtracted 9/4. Now, put this in its proper vertex format. Goes in here.
X minus 3.
No, it's always x minus whatever number you got when you divided that by 2.
Oh.
So it's 3 halves squared. In other words, because we completed the square, we know that quadratic factors this way. Always will. That's the whole reason you complete the square, is so that I can write it as a binomial term squared. Now, 2 minus 18/4 is minus 2 1/4, or minus 9/4. So this is our final vertex format. Where's the vertex at?
3 halves and 9/4.
Good. Minus 9/4. Okay. That was the last one, so I got to go to 716. Back to trig. Hold on. My dog got trapped. That's funny. Give an exact measurement if possible. Each measure is given in radians. What they mean by that is that 4 is radians. This is something that's hard to get used to. Okay? Down here, when you see 4 pi over 3, you expect that to be radians, right? right?
Yeah.
It's because there's a pi in it. If I wanted it in degrees, I would write 240 degrees for that 4 pi over 3. So the fact that there's no degrees there and there's a pi in it always means that it's in radians. Well, sometimes it can be in radians without the pi, like that one. Sine of 4. Now, we take sines of angles to get ratios. But that angle of 4 radians, put that in your calculator. Is your calculator in radian mode?
I can put it in radian mode.
Put it in radian mode and take the sine of 4.
Negative 0.756.
And notice that 4 pi over 3 is in the third quadrant, right? Well, what is 4 pi over 3? 4 times 3.14, that's pi, over 3. That's going to be a little bit more than 4, right? What is that number right there? Just that. 4 times 3.14 all divided by 3.
4.186.
Okay. So I could have expressed this instead of 4 pi over 3. I could have said the sine of 4.18. Still radians, still's the same answer. In other words, I'm still looking for an exact answer, and I've got one here. 4 pi over 3 is the equivalent first quadrant angle is pi over 3, which is 60 degrees. So this one is negative square root of 3 over 2 because it's third quadrant. Okay, so in the bottom problem on this page, I can give an exact answer, and I can also give a rounded answer. I think you said it was 0.8 something before. 84, I believe. Here's what I'm trying to say is that, I know how to do this. Got this neat little toy. I think I told you about it yesterday. Question is, oh, that's what I want right there. I could write this one as sine of 4.18. Then it looks an awful lot like the first problem, does it not?
Yeah.
In other words, you don't have to have pi for it to be in radians. That's in radians even though it says 4. It's hard to relate that to pi, and there's no need. In other words, your calculator will accept radians without a pi in it. It just did. You took the sine of 4 radians and you got minus 7.56. Well, when I take the sine of 4 pi over 3, I know I should get something close to 0.8 because I know the exact answer is minus root 3 over 2. And I will. Take the sine of 4.18. You're going to get minus 0.8 something. Leave it in radian mode and take the sine of 4.18.
Negative 0.86.
Yeah, very close. to what we got for the sine of 4. Now, you want to be confused. I had a student the other day who goes to Evelyn, and they were doing sinusoid functions, and they were doing that. And man, it drove me crazy. I didn't know what was going on because I thought that was in radians. I thought it was 10 radians. So I did the whole problem and got a nonsensical answer. And finally I said, what's going on? He says, oh, that's degrees. They hadn't labeled it degrees. They had left the degrees off. But at the Evelyn, at the moment, they haven't really gotten into radians. So they had only taught trig in degrees. And he didn't really, they had mentioned radians, but hadn't really gotten into it, clearly, because they never would have written this problem this way. In other words, if they meant degrees, you got to put degrees there. Because if you don't put the degree marker, that means radians. And it should have been 10 radians, but they meant 10 degrees. So you got to be careful. You can take trig functions of radians without a pi in it. Just know that. Now, it says give an exact measurement if possible. Well, it wasn't possible with this one. I don't know what the exact answer is. I know it's some ratio, but first of all, I would have to figure out what that angle is. What is 4 radians? Well, I know 2 pi radians is 360 degrees, right? So 4 radians, if I convert it using the normal method, I get 180 degrees per 1 radian. The radians cancel. So that's actually 720 degrees. That's weird. That's really weird. Ah, it's 180 degrees per pi radians, not per 1 radian. This is the normal conversion factor, if you do it the way they teach you in school. Every time you're converting, you're either using 180 over pi, or if you're going from degrees to radians, you're using pi over 180. So this answer actually is 720 over pi degrees. Well, I don't know the exact answer to that, nor do I have any way of figuring it out. First of all, pi is an irrational number, so if I divide 720 by pi, I'm going to have to round it off. I'm going to get a non-repeating decimal. It goes to infinity. So there's no way to get an exact answer. The best I can do is just put it into the calculator in radian mode, the sine of 4. And that gives you an answer that at least is an approximate answer. I did give an exact answer on the sine of 4 pi over 3. That was negative root 3 over 2. All right. How come we sometimes have all this stuff at the bottom? Is this? Oh, I see. That's a graph of this. What's the blue line? Why do they have a blue line?
For y equals 0.5.
Okay. In other words, to solve this equation, is all I have to do is make one equation be sine of theta and the other equation be y equal 0.5. That's what the blue line is. Wherever they intersect are my solutions. Okay, what's that intersection point equal? Hold on. Let me read the exact values of the angles that are the solution to that. So they want you to do this hard way, which is to read the graph. And that is a hard way because that, and to make matters worse, they've labeled their horizontal axis in numbers, not in terms of pi. However, do you know what that value is? Where's the sine of what angle is equal to 0.5?
30.
Which is how many radians?
1 or
Pi over 6.
yeah.
Remember, these two numbers have to multiply to be 180.
Yeah.
So if you know it's 30 degrees, you know it's got to be pi over 6. What other angle? And let's just go from left to right. That's 30 degrees. What angle is that right there? In other words, that's the second quadrant angle. What's the
180. 150.
correct? And 150 is 5 pi over 6. Notice why. Pi over 6 is 30. 150 must be 5 of those. Are there any other places in the unit circle where this is true?
No.
No, because my unit circle ends right there. Oops. Wow, it let me mark on that. Oh, that's because I'm logged into your website. Okay. I didn't mean to mark that. I don't know how to undo it. However, there's always going to be more. In other words, it didn't restrict the domain to 0 to 2 pi. It said find the exact values in radians. So far I've got 2 of them. What's the next one? In other words, what's this one that I'm pointing at with my mouse? I can't make that go away now. But there's another point where they cross. What angle is that?
210.
Add 2 pi to that number right there. In other words, trig, sine waves, every 2 pi, you got another answer. So if I add 12 pi over 6 to that, I get 13 pi over 6. Now add 2 pi to this one, what do you get?
17 pi over 6.
And I could go on and on forever. In other words, now I'm going to add 2 pi to that one. So I get 25 pi over 6. And I'm going to add 2 pi to that one. So I get 29 pi over 6. Now let's figure out a way to describe this without having to write to infinity. Because at this point I got to keep writing to infinity. There's a method they must have taught you, otherwise this wouldn't have been in your question. It's pi over 6 plus multiples of 2 pi. Now they may use k instead of n. Do they?
No.
This is an infinite series. That covers that answer, that answer, that answer, and all the answers out to infinity. Now, to describe this infinite series, I got to use 2 equations. The next one is 5 pi over 6 plus multiples of 2 pi. So there are the 2 answers to their problem. And I have to use 2 equations. I cannot describe this series with 1 equation. The series goes 1 5, 13, 17, 25. You can't describe that with one single concise equation, but you can describe it with two equations. The key thing to remember here is when you get your 2-unit circle answers, which are these two answers, those are the answers in the first unit circle. Well, the way you get all the rest of them is you add 2 pi to that, and you add 2 pi to that, and then you add 2 pi to that. In other words, you're leapfrogging every time. And now you try to figure out how to write the sequence pi over 6, 13 pi over 6, 25 pi over 6. Well, that's pi over 6 plus n pi. Now when you use the letter n here, it has a very, plus n2 pi, excuse me. When you use the letter n, it has a very specific connotation, and that is that it's all integers from negative infinity to positive infinity. But it's integers only. N cannot be 2.1. And every answer I have up here is 2 pi bigger than the other side of the red curve. So that works for that series, and this works for the 5 pi, 17 pi, 29 pi series. And that's the way you have to do these. And the way to do them easiest is to figure out at least 2 unit circles. I don't know that I needed a third. I did that just to make it a little clearer. But 2 unit circles, in other words, just these 4 answers, will allow you to come up with the 2 series that I came up with. But you should always do 2 unit circles. What the reason they're doing this with a graph is, I don't know why. I guess to make it more comprehensible. I'm not sure it is, but anyway. Wow. I'm reading all of this just in case you're wondering why the silence. Notice how they stress the 30, 60, 90 and the 45, 45, 90 triangles that I keep trying to impress upon you to memorize. I think you have. All right. Let's complete this table. 30 degrees is pi over 6 radians. What's 45?
Pi over 4.
What's 60?
Pi over 3.
It's 90?
Pi over 2.
It's 120.
2 pi over 3.
Copy and complete a table like the one below for all special angles between 0 and 360. So the next one is 150.
I'm pretty sure you could probably skip this. I have this circle mapped out, which every angle like that mapped out.
So you're pretty good at this?
Yeah.
You think we can skip this?
Yeah.
Okay. Good, because that was getting to be rote. The next problem. In other words, I felt like you knew all that anyway. We spent a goodly amount of time teaching you the unit circle last time, and I think you learned it. It really, I can teach somebody the unit circle in 30 minutes. Anybody. By doing it the way I did it. And you got it. In other words, you didn't have to memorize all 16 slots of the unit circle. You memorized a way to figure them out. That's the way to do it. Draw a picture of an angle that measures 6 radians. What does 2 pi radians equal?
I don't know.
Oh, what's pi equal?
3.14.
Okay, so that's 6.28 radians is what it is.
Oh.
On an angle that's 6 radians. So how would I draw an angle that's 6.28 radians?
I don't know.
360 degrees, right? 2 pi radians is 360 degrees.
Yeah.
So 6 radians would be slightly less. So 6 radians I'm going to draw, hold on, I'm going to draw an angle that's not quite 360 degrees. That is 6 radians approximately. In order to draw it exactly, I would have to convert it. Okay, how would I convert it? Well, I got 6 radians. What's the conversion factor?
180 over pi.
180 degrees over pi radians. And that's important because I know I want to lose my radians and get to degrees. Well, that's 1080 over pi degrees. You have your calculator?
Yeah.
Divide 1080 by pi. What do you get?
343.
That's what that angle was that I drew, 343 degrees. Ah, I see. Draw a picture of this. Approximately how many degrees is it? I guess I could have converted it to degrees first. I kind of wanted to go through that analysis though, because a lot of people don't get that pi is just a number. So when you say 2 pi radians, they don't know what that converts to. But remember, pi is 3.14. And so I can always convert a radian that's in pi into a number. So 6 radians is not that different than 2 pi radians. It's a little different. It's only 343 degrees, whereas 2 pi radians would be 360 degrees. So that angle right there is a 17-degree angle. Using only your picture, estimate the sine of 6 radians. Well, here's what we're going to do. We're going to use only our picture. Let me redraw the picture a little bit bigger over here. How much time we got? We got 6 minutes here. There's my angle, all right? That's 343 degrees. But if I want to estimate the value of the sine of this big angle, I can analyze the reference angle, and I can do it by drawing a triangle, like that. Well, theta, which is 17 degrees, is that angle there. What's the sine of 17 degrees? Approximately. It's the opposite over the hypotenuse. Well, the hypotenuse is 1. We're in a unit circle. And this measurement right there, who knows what it is? If my hypotenuse is 1, that looks to be about a third. So I'm going to estimate that the sine of 17 degrees is a third, but it's in the fourth quadrant. What is its plus or minus sign?
Negative.
So over here, the sine of 6 is guessing negative a third. Now tell us what it really is. Go in your calculator and see.
Negative 0.96.
I don't think so. Sine of 6. Make sure you're in radians.
Oh, sine of 6. Yeah, negative 2.79.
Negative 0.279.
Oh, yeah. Sorry.
And the reason I knew that is because the sine of any angle can never be greater than 1, or can never be less than minus 1. In other words, remember what the sine curve looks like. It looks like this. Notice that it's never greater than 1 or less than minus 1. Now, if I put a number in front of it, like 3 sine of x, well, then that can go up to 3 and down to minus 3. But if I'm talking just the sine of an angle, never can be greater than 1, never can be less than minus 1. So I knew that the sine of 6 could not be 2.79. Had to be 0.279. And that's relatively close to my guess. My guess was minus 0.3333. And my guess was based entirely on estimating that that distance was about a third of the hypotenuse. In other words, if that was 1, that's maybe a third. So the sine of theta is the opposite over the hypotenuse. I don't quite understand their purpose of this question, but once again, mine's not the reason why, but to do or die. Let's end it at 793. Make a mental note so we'll know where to start next time. Or make a note. All right, Nicholas. Have a good weekend. I'll talk to you next time.
Okay, you too.